Okay, so continuing from the previous video, let's just kind of move along. We're going through the introduction to the course. So these are some of the prerequisites to the course. Yeah, it's all just kind of fun elementary math. We can talk about all this stuff. It would have nothing to do with our grade in elementary statistics, yeah. But these are integers, positive and negative. We say that it goes to infinity. We say that it goes to negative infinity. We might recognize a little something that we call the number line. So it's just whatever they assign. I kind of like to make a little video out of it, even though it has very little to do with statistics. Yeah, but we have the number line 1, 2, 3. Everybody's seen the number line 2, 3, 4, 5, -5. Yeah. So these are all the integers. Yes, those are the integers. I'm just wondering, we don't care about natural and whole numbers. We'd have to Google them, but you have natural numbers and you have whole numbers and things like that. One of them, there are positive numbers, but one of them contains 0 and one does not. Uh, in fact, the question that they're asking us about there are going to be the natural numbers. Yes. So if we talk about the set of all whole numbers, yeah, and if we talk about the set of all natural numbers, these are just silly little definitions, but this is how they define it. Yeah. Okay, natural numbers are all positive integers, 1, 2, 3, 4, to infinity. Okay, so the whole numbers are the same, except they include 0, 0, 1, 2. These are the whole numbers. Oh, we don't want to get the definition wrong. I'm just pretty sure that a whole number is the set of all positive integers and 0, infinity. Yeah. So the whole numbers literally contain 0. The natural numbers are all positive integers, but they do not contain 0. So the natural numbers, which is what they're asking for right there, is going to be all positive integers. They have to be integers. And the square root of 4 equals 2 is an integer, yeah. So these are kind of our basic sets. We have, it starts with, just erased it. It starts with the first one, which are natural numbers. Yeah, 1, comma 2, comma 3, comma 4. And then after that, we have this set of all whole numbers. Natural numbers might be like a capital N. Whole numbers might be like a capital W, the set of all whole numbers. Yeah, which equals 0, comma 1, comma 2, comma 3, comma 4. Yeah. And then if I miss one or two things, who cares? We have the set of all integers. Yeah, which is going to be 0, 1, 2, 3, -1, -2, -3. Contains negative integers. I don't know if we're allowed to say negative integers. I guess we are. Yeah. But the set of all integers is the one we can't say like a negative whole number. It doesn't exist. All of us, including me, we never know exactly how to say it, but we basically know obviously what the integers are. 0, 1, 2, 3, 0, -1, -2, -3, between negative infinity and infinity. Yeah. So then that after that is where it gets messy. Okay, now 2 over 7, that's a rational number. After that, after the integers, we have R, fancy R. That's a fancy R, which is the set of all rational numbers. Now it gets fun. Before it wasn't fun. Yep, we don't need it for the problem, but this problem reminds me of all of this, so might as well make a video on these. So in number theory, this has a definition. Yeah, not all fractions, not like the square root of 5 or something. That's irrational. But how do we define all rational numbers? Anyways, R equals A over B. So rational numbers do include all fractions. Yeah, R equals A and A over B. I guess yes. Such that A comma B, we say, do we use one of these? Rational numbers. I think Z, I have to review, but I think Z is the integers. Anyways, this whole notation, please ignore that there. but A and B are integers. Yeah, A and B are integers. Okay, so that's what a rational number is. If A is any integer and B is any integer, where of course B is not equal to zero because we can't divide by zero, all rational numbers are going to be all fractions where A and B are integers. The top and bottom is an integer. So basically, the square root of 5 not allowed, the square root of 3 not allowed. But as long as, everything in R, an integer divided by an integer, that's how they define a rational number. In this thing right here, 2 over 7, that's obviously an integer. 3 halves is an integer. If you have 2 over 1, which is an integer, which equals 2, I'm sorry, 2 over 1, which is a rational number. What did I say integer? Yeah, I'm saying it wrong over here. A rational number. So 2 over 7 is a rational number. 3 halves is a rational number. What if I have 3 over 1? That's a rational number. That equals 3. All the integers are also rational numbers. They do the set theory where you have the set of all rational numbers. Yeah, which is any combination of A divided by B, but you have the integers are contained within the rational numbers. All integers are rational numbers. All rational numbers are not necessarily integers. So a rational number is just an integer divided by an integer is all that is. Yeah. And then we have the fun one, we have the irrational numbers. The irrational numbers, it's just, if you take a number line, I mean, we can't really do this, but it's one way that they define the irrational numbers. Yeah, if you have a rational number, which is all possible A over B, where A and B are integers, everything that's left is irrational. So basically the square root of 3 divided by 2 is irrational. Anytime you have a radical and you can't do the radical, anytime you have a radical and we cannot do the radical, it's automatically irrational. So we know that we cannot do the square root of 3. So be careful, they have it basically in there. What if we have the square root of 4 divided by 2? Well, the square root of 4 is 2 over 2, which equals 1. So that's rational. It's also technically an integer, yeah? So if you have a square root, or any radical for that matter, you could have a cube root of 7. That's irrational. If you have a square root or any radical symbol, third root, fourth root, fifth root, seventh root, yeah, that you cannot do, you cannot simplify it, then it's automatically irrational. If you can simplify it, it might be rational, yeah. So anyways, they just want all the natural numbers. Yeah, they just want all the natural numbers, which are going to be the positive integers, yeah. So remember, the square root of 4 equals 2, so that's an integer. 3 is an integer. So those are both natural numbers there. Hmm. Stupid. Okay, so what do they say here concerning everything we just said? It starts with whole numbers. Just want to kind of review. It starts with whole numbers, yeah. And then it goes to what? It goes to, nope, it starts with natural numbers. I always forget. Natural does not contain 0. The whole numbers do contain 0. And then it goes to integers. Yeah, as we just said a moment ago. Yep, then it goes to rational. Then it goes to irrational. How many sets do we come up with? 1, 2, 3, 4, 5. What do they have written here? Whole number, natural number. Oh, real number. We didn't say real number. Irrational numbers, rational numbers, and integers. Okay, they had 5. Okay, yeah. So the set of all real numbers includes, if you have all rational, it's a technicality if we can kind of do it in our head. But if we have the set of rational numbers, and if we have the set of irrational numbers, all that exists, if you add those, if you add all the rationals and the irrationals, not add them, but if you put them together in one set, it actually creates the number line. So the entire number line, not just the integers, but if we think that there's infinitely many numbers, of course there are. Yeah. So every number on the number line is a real number, yeah. We don't want to go there now. What is a complex or imaginary number? If we remember that, I, that's going to be any number of the form a plus bi. We just don't want to go there now. It has nothing to do with the class. But yeah, the real numbers basically contains everything except not complex numbers. So they can ask us a fun-filled question here. The answer is move on. It doesn't matter. Okay, so we do powers. This is kind of, if anybody memorizes the powers of 2, it's just kind of jogging my memory. Already the powers of 3 get hard, but these little things seem meaningless, but they're kind of a little bit useful later on in math. Yeah, 64, 128, how high can we go? Yeah. So these don't really matter here. We don't really have a trick for this. We would always just do this on the calculator. We don't want to do any nifty algebra, unless, of course, we do 6 cubed, yeah, which is a 2 times 3 quantity cubed, which is a 2 cubed, 3 cubed, which is going to be 8 times 3, 9, 27. Yeah, so that doesn't really help us at all. 7 times 8 is 56. So that's 16, 17, 19, 20, 21. Yeah, but anything in this class we do on a calculator, we don't need any algebra. So they're doing some review. All they're telling us is that that's negative 11 squared. I know there's no parenthesis, but whenever they square anything, we're supposed to know the negatives on the outside. As opposed to this, it's not this. If you have negative 11 quantity squared, you have negative 11 quantity squared. Yeah. Yep. If you have negative 11 quantity squared, the negative is on the inside. Yeah. But if we have this here, it's simply understood that the negative is going to be on the outside. Okay, good. So scientific notation. We go 1, 2, 3, 4, 5, 6. Whenever a smaller number gets bigger, it becomes 1 times 10 to the negative 6. The point is to get rid of the zeros. Yeah, so there's only 2 possibilities. The small number becomes bigger, in which case it's to a negative power. The power is the same number of places that we move the decimal. Yeah. Okay, good. So they followed up with one of these, yeah. But we have 6.53 times 10 to the 4. We have to make more zeros. We can skip this step. Everybody does this in their head. It's perfectly okay to skip this step. How many zeros do we write? Too many is fine. We don't need that many. But if it's to the 4, you move it 1, 2, 3, 4, and it's 6, 5, 3, 0, 0. Yeah. We would just do this on a calculator, so it really doesn't matter. If they say 3 sig figs, because I know for a fact they just kind of review all the basics. It's not chemistry, but it comes from chemistry. But it doesn't matter math, physics, chemistry, statistics. There's a very small palette that's similar in all of it. And 19 over 99, we actually can do that by hand, which of course we would never do. Yeah. But if you do 19 over 99, it's going to be approximately 0.19191919. If any of us remember from elementary school, it is correct to put 0.19 with a bar over both, yeah? But 3 sig figs, and the 0 to the left of the decimal never counts. If we ever have 0.023, when it comes to any number less than 1, the zeros on the left never count. That right there is 2 sig figs. So we're not going to start reviewing a bunch of sig fig rules. It would take too long. It has nothing to do with the class. But you have that right there. Yeah. But this is not significant. If they say round to 3 sig figs, I see 0.192. So things like this will come into play. We have to know the most basic, basics of graphing, the basics, if that makes sense there, yeah. But if we have a graph, we go 1, 2, 3, 4 this way, 1, 2, 3, 4 up. The vertical is always y, the horizontal is always x. And if we go, 4 that way and then 4 that way, we get the point. That's not the point. Yeah, we get the point 4, comma 4, yeah. We can see the point right there that we did. So it's extremely difficult to teach the basics. We don't care about all those sets of integers and all that. We don't care about the definition of a rational and irrational number. But when it comes to the most basic pre-algebra, everybody has to know it. So I know that we don't need this. If we really, really need this review, then we're really going to struggle in the class. Yeah, so they're just telling us that we have an xy point. All points are of the form xy. What is negative 5, 3? 1, 2, 3, 4, 5. Negative 5 up 1, 2, 3. That's the point negative 5, 3. It's basically 5 left, 3 up. But they just want us to know that the left slot is an x. The right slot is a 3. So we're going to do some statistics, not yet. I've been through all of this, obviously. I just don't feel like reading this. So we'll kind of conclude with this. They're going to have us read some basic graphs like this. The graphs do get harder, yeah. But in baseball, a grand slam is a home run with the bases loaded. The top 5 numbers of career grand slams for Major League Baseball players are illustrated in the figure, blah, blah, blah. We're supposed to know what they're talking about, still active. The number of grand slams, okay. Those are going to be the players. Okay, so they do a graph over there in the far right. The number per player. Estimate players A's number of career grand slams. The number of career grand slams player A is 24. Okay, so of course, just testing us on whether or not we can read the graph. The height there is 24. So B, who has the record number of career grand slams? What is the number of grand slams? Obviously, it's going to be C. I guess we're assuming 28, which is kind of hilarious. Of the 5 baseball players listed in the figure, player B is the only active Major League Baseball player. Okay, so they say that's still active. Estimate how many grand slams he needs to tie the record. Okay, good. So we're seeing 25 is what the B currently has. Yeah, I'm going to say that B currently has 25. Yeah, so we're going to say apparently the record is 28. Are we to say 28 minus 25 equals 3 more he needs to get the record? And true. Okay, so we are trying to be a little bit thorough. I think after this, there is going to be one more introductory set of exercises. So we'll tackle that in the next video.